morning, good morning. Welcome back. Glad to see everybody's here safe and sound. Some kind of scary weather this morning, so we had a delay. Any class you had that started before 10 o'clock was canceled, so maybe you contact your teacher or maybe they sent you an email to let you know what the new plan is. So we start today on page 13. If you could open your packets to page 13, that would be great. And we'll start by looking at our calendar here. So today we are covering 6.1 graphical and numerical antiderivatives, and just a heads up of some things that are coming down the pipe. This coming Friday, project number 1 is due, okay? Project 1 is due on a Friday. I do accept the projects up to 1 week late, but there are penalties associated with turning it in late. So try to get it done before the start of class on Friday if possible. And then Monday is our very first quiz. Any questions on the calendar? Okay, so one non-calculus announcement. UMass Amherst would like to extend an invitation to join them for their upcoming Career Blast 2013. Jump down to this part here. With approximately 140 employers currently registered, they are expecting record numbers this year. So it's a career thing. There will be lots of people to give resumes to and get information about local companies. There's a website here that you can go to see an exact list of the companies that will be there, and it's free and it's open to the community. So think about it, and it's happening on Wednesday, February 20th, 10 until 3. I don't think you need to be there the whole time. I expect it's you go and you walk around to the tables that you're interested in and then you leave. But I do not intend to bring this back up again like on February 19th. So if you're interested, write down something right now. You can ask me about it. I can give this to you. I suspect that all students got this, but I don't know. Anybody recognize this stuff? It went in an email. I got it in an email, so I'm assuming that you guys got it in an email too, but I don't know. All right, so we're again on page 13, and we'll jump up here to number 1. We'll go to Nikki. Okay, so we'll start off with an easy one. What's the derivative? X plus 3. Chris, can you read the next part? Okay, this is a really important word. Antiderivative means take the opposite of taking a derivative. The antiderivative of 2x plus 3 is the function whose derivative is 2x plus 3. So all the derivative stuff we did last semester, we're now going to start working the other direction, work backwards. Somebody had some function up here, they took a derivative, and we know what they got at the end. And we're trying to figure out what they started with. Does that make sense? Do you see something in this problem that if I just give you the 2x plus 3, there's no way for you to know what part of this answer? That constant, that plus 2, right? Because when you took the derivative of that plus 2, it went to 0, but the derivative of plus 17 would also have gone to 0. So can you write down a different antiderivative of 2x plus 3? Go ahead. Josh, what was your favorite constant? Oh, that's very fancy, but let's pick a number first, then we'll do C. E. Perfect. So that is an antiderivative, right? What does it mean? It means if you take the derivative of this thing in purple, x squared plus 3x plus e, you should get 2x plus 3, and you do, okay? So it's going to be more complicated doing antiderivatives than doing derivatives. However, there is always an easy way to check your answer. What can you do with your answer to see if it's right? Take its derivative. And if you get what you started with, then you got it right. If you get something different, it's not necessarily going to help you fix it, but you'll know it's wrong, right? Taking antiderivatives is significantly harder than taking derivatives, but you can always check your work by taking a derivative of your answer. Okay, we'll go to 3. Josh? Thank you. Joey? Okay, you've got 2 parts, A and B. Check in with your neighbors. Okay, any luck on cosine of x? Where did it come from? Sine of x. What's a good name for sine of x? F of x. We are going the opposite direction, right? We have a derivative given. We want to figure out where it came from. What's missing if I wanted the general antiderivative? There's a plus c, right? You can pick any number you want to and add it out there or subtract it out there. The general one is a plus c. Okay, part B is a little bit tougher. Where did 4x cubed come from? It came from x to the fourth. Did anybody else get that? X to the fourth, okay. And what about this other one? It looks a lot tougher. Yeah, it's tough. It's easy if you know where it came from. It's impossible if you don't know where it came from. It's just one of these kind of miracle things that if you recognize 1 over 1 plus x squared, we've seen that derivative before. If you recognize that, then it's really easy. It came from arctan. Nothing more and nothing less. But if you didn't have a sense that it came from arctan, I'm just looking at 1 over 1 plus x squared. What can I take a derivative of and get that? I have no idea. I didn't even know where to begin. So there is something kind of miraculous that has to happen for a lot of our antiderivatives. You just have to know some derivatives really well so that you can do these antiderivative problems. Okay, what are we missing at the end? Plus c minus c. Let's be really fancy and call it a d. Any constant over there, right? Any constant, but make sure you include 1. And then again, what's a good name? F of x. Okay, we're going around to Topher 5. Okay, your choices are velocity and position. Be very careful as you put them into the two blanks. Okay, which one goes first? A few votes for position. So that means velocity goes over here. Is this right? Position is an antiderivative of velocity. Is it true? So it is true because the derivative of velocity is position. This is just saying it in the other direction. Number 6, Travis. Okay, so 2t plus 3 is the velocity of some object at time t. And we know now how to find a position. How do we find the position given the velocity? We take an antiderivative. Okay, so let's try it. So what's a good name for the position function? I think there's a letter we use in physics. It's s. So s of t equals, take an antiderivative of 2t plus 3. Is this the same one we did up above? Yep. So what's the antiderivative? T squared plus 3t, we'll call it. Yeah. Okay, great. So there's the position. Plus c. So we don't know what the c is. We don't have any more information here. So we can't tell where the object is, right? If we knew, for example, that c was 7, just making up a number, then how would you find the position 2 seconds into this experiment? You'd plug 2 in and get what you get. Another way you could do it, I think this is what Topher was saying, is that if you just ignore this, plug 2 in, but then it starts at 7, so it's 7 more than whatever you get. Does this make sense? Okay, so it's not enough to just know the velocity. You also need to know, it turns out, the initial position. Okay, so let's move on to the next page, and we'll start thinking about graphs. So we will go to Alex, number 7. Alex. Okay, so this graph again is f prime. It's written out here. And the question is, what does the graph of f look like? So I've highlighted a few different characteristics of f prime. I'm not saying they're all important, but just pointing out that, for example, here f prime is increasing, and there f prime is at a maximum. And here f prime is decreasing, and this guy right here is not only the x-intercept, but it's also a point of inflection for what it's worth, okay? So we've got lots of attributes of f prime because we can just look at the graph and read that. The question is, how do we find the graph of f? And I think that we actually spent a little bit of time last semester doing this, so let's see if we can refresh our memories. Tell me what is true about this function that's graphed here, this f prime, for this entire space. Is it increasing the whole time? F prime, the graph you were looking at. What's true about it the whole time there? It's positive, right? If f prime is positive, what is true about f? Is increasing. If f prime is positive, f is increasing. You think about it, if you have a graph that's going up, then all the derivatives, all the tangent lines will be uphill, all be positive. So this entire time, the graph of f that we're about to draw down here had better be increasing. So we're going to draw something that's increasing. Where does it start? No idea. Pick your favorite point. I'll start mine right here. But I'm going to draw something that's increasing. Now I'm going to make a couple of attempts at this. So if you have a pen, you might want to hold off or write lightly. But I got to draw something that's increasing the whole time. So for example, that is increasing the whole time. Yes? Okay. And then what happens? What's true about f prime in here? It's negative. So then in this entire space here, what's true about the graph of f? Must be decreasing. Okay, so then the blue thing had better be decreasing. Let's go back. So all of this space right here is going to be decreasing. So we better draw something that's decreasing. My function isn't really ready to just decrease from that point. I think I didn't draw it right, right? It would be a very dramatic change right there if all of a sudden it was increasing, 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 and then dramatically changed its mind. Okay, so then probably it wasn't exactly what I drew. So then what's the other way I can draw something increasing different from what I did here? Is make it concave down. So let's try that. So I'm going to draw increasing concave down until I get to that point, which is somehow not above. It should be right above this point. So increasing concave down until we get to that point. And then because f prime is highlighted here in green is negative the whole time, f is decreasing the whole time. And this feels much more natural to me. It was ready to turn around. Okay. Okay, so maybe there's a third way that we can draw something that's increasing. So I think what I heard Topher say is that we could maybe make it increase this way and then increase that way. Something like that, like a logistic. Yeah, that's a good catch. Right, it looks pretty smooth. So the question is, well, which one is it? Is it just entirely concave down, or is it concave up and then it transitions to concave down? And I think Topher said it. Can you repeat what you had said again? Everybody hear what Topher said? It's complicated. Repeat it again. Yeah, I think that's true. And another way to say that is that this point right here is the biggest value of f prime. Yes? That is the highest that f prime ever gets. And if you're looking at the place where the f prime is as big as it will be, you're thinking about a tangent line that is what? The steepest it will be. It's the biggest slope. It's going to be rising at the fastest rate at that point. So somehow at this spot right here, we need to have the steepest tangent line. So let's see if we can undo. I told you I was going to make a few attempts at this, right? So we need it to be increasing the whole time. That's what it's been for all of our attempts. But we needed to have the steepest tangent line at this peak right here. So we're going to draw something that's getting steeper, steeper, steeper until it hits there. It's still going to go up, but it's going to go up and not be as steep as it has been. So I think something like that is the most accurate that we've drawn so far. We don't. So one of the things that I had said is pick your favorite starting point. I started it there. You could just as well start here or up here. Yeah, this is that plus C part that we just don't know. Okay, so observations. If f prime is positive, like the entire yellow, what's true about f? It's increasing. And if f prime is negative, like in the green, f is decreasing. Fair enough. But then we've got this additional thing about the concavity. What was special about f prime that made our graph concave up in the beginning? F prime was increasing. F prime was increasing, the graph was concave up. It's important enough to write down. I'm pretty sure I did. Could it be somewhere? Here we go, number 9. If f prime is increasing, then f is concave up. If f prime is decreasing, then f is concave down. Okay, so then perhaps I can fix my second part of the graph. Maybe you can fix my second part of the graph. The second part of my graph over here, I just drew something that was decreasing, but I didn't really pay much attention to concavity. So can you draw something that has the right concavity? It's got to be decreasing the whole time, but see if you can figure out where it changes. Okay, so what we just saw on the previous page was that anytime f prime is decreasing, then f must be concave down. So until we get to here, we better draw something that continues to be concave down. So this part, decreasing and concave down. But then as soon as we pass that point, and we go this way, f prime is now increasing, which means f is concave up. So then we draw something concave up. And in fact, ready to turn around again. Where does f turn around and start to go back up? It's right there at the place where the derivative is 0. So then it's going to start to go back up. There's a lot of pieces to put together. Okay, Nikki?
We have to be careful about proportions. If we go down that far on the right,
Yeah.
just below the x-axis, we have to make sure somehow that it hasn't gone down too far though.
Yeah. Do we think the ending part of my graph is down too far compared to the beginning of the graph? Oh, yes. Yeah, there's a symmetry happening on this thing. It looks like a sine graph, and so it feels like whatever the function was doing here, well, it's got like the exact corresponding but opposite thing happening there. So I think it's absolutely correct to say that I really shouldn't have ended it down here. Probably should have ended it right at the same y equals 0 that I started it. And if I had started it down here, it probably would have ended at the same y level as it started. So absolutely. We're looking for just a rough sketch. This is a very good detail that you found. It turns out that the thing that decides exactly how much we go up or down has to do with the space between. And so we're going to come to that later today. But for right now, I'm content with my rough but inaccurate sketch. Thank you. Okay, and last thing about this graph that I had labeled was this point of inflection. So if it's a point of inflection, what derivative does point of inflection have to do with? Is the second derivative? So I am saying that the second derivative of this pictured function is equal to 0. What's the second derivative of f prime? It's really f triple prime. Do we buy that? It's the second derivative of that function that we're looking at. And that function is already one derivative on its own. So really we have information about the third derivative. does information about the third derivative play out on the graph of the original function f, which is what we've sketched here? Anybody remember the name for the third derivative? There was like position, velocity, acceleration, jerk. Right. So did f triple prime come up at all when we were graphing functions? The answer is no. So point of inflection on f prime doesn't really come into play, not for our rough sketch. All right, there's another example right down below. Can you guys do your best to try to draw something? Again, looking for a rough sketch. Check with your neighbors, and then we'll come back together. Okay, we'll come back together. Some folks decided to start their graph right here, which is their prerogative, but leads to bad news because you run out of space. So let's start low and say that the entire graph of f prime is what? Positive. F prime is positive. So f is always increasing. So the question is, are we increasing concave down? Are we increasing concave up? Or are we doing some combination of the two? This is where we look at the increasing, decreasingness of f prime. So in the beginning, f prime is decreasing. And we wrote down on the very next page that if f prime is decreasing, f must be concave down. So the beginning part is going to be concave down. So we draw something, so f is concave down. So we draw increasing concave down until we get to here. Increasing, but concave down until we get to there. And then the rest of the time, f prime is increasing, so f is concave up. So we draw something still increasing, but concave up. Questions on that? Okay. On the next page at the top is a challenge question. You can give that a shot later. We're jumping down here to number 10. And I think we're back to Evan. Thank you. Vince? In. So we're going to fill in that table. So suppose that we didn't have the table to fill in. This is the same exact question that we just answered. I'm giving you the graph of f prime. I'm trying to get information about f. So in the beginning part, f prime is what kind of number? Those are all negative numbers. So if f prime is negative, f is decreasing. So we're going to draw something that is going down in the beginning. And then what's true about all the rest of these f prime numbers? They're all positive. So f for the rest of the graph will be increasing. And then the only other piece is the concavity. So I think it's important to make sure you look at the right thing first. The right thing to look at first on f prime is where is it negative and where is it positive. And the second thing has to do with concavity. What is f prime, this picture, doing from here to here? It is increasing, which means that f is concave up. Right? So we could draw a rough sketch just like we did on the other one. You'll have lots of practice with that in the group activity today. But we're going to get to Nikki's observation from before, is can we be a bit more accurate than just saying, oh, f is increasing here and concave up, and then it's increasing but concave down. Can we be more precise? The answer is yes. So let's take a look at what the fundamental theorem tells us here. So the fundamental theorem, part one anyway, as Evan points out, says the following: the integral of f prime of x dx from a to b is equal to, can you guys fill in the blank? Fundamental theorem starts with that. The a and b will be in the rest of this equation for right now. So what is it equal to? f of b minus f of a. This is the fundamental theorem part 1. It is so named, it's important. You guys should know this equation. You used it during the homework last night. We're going to use it again right here. Okay, how are we going to use this? Well, let's just plug in some numbers. For example, if I wanted to do the integral from -4, which is given to me up in the problem. See how it says f of -4 is 0? So I'm going to put a -4 here, and then I'm going to look at the table and see that the first number is -3. So for reasons that might not be clear to you at this moment, I'm going to start with those two numbers. The equation is true for any two numbers, but I'll pick these two. F prime of x dx equals, go ahead and fill in the equation. It's f of something minus f of something. Just have to go get the right number first. Which one goes first? The one on top, the -3, minus f of -4. So if we believe the fundamental theorem, then we believe this is true. Now this integral symbol, forget about the fact that there's an f prime in there. This integral symbol just means one thing in terms of a picture. What does that integral sign mean to us? It means area. So if somehow we can find the area in that picture from -4 to -3, then we will know what this left-hand side is equal to. It's just a number. So let's take a look at the picture. From -4 to -3 is here. We're looking for the area between the curve and the x-axis. What is that area equal to? It's equal to -1. Use your triangle area formula or count boxes. So the left-hand side down here is -1, right? I appreciate, I'd said area is -1. So technically area is 1, but the integral is -1. So we can start filling in. This red equation becomes this integral sign is equal to -1. F of -3, I don't know, but that's what we're after in the table. Minus, how much is f of -4? It's 0. That's given in the problem. So f of -3 is -1. Buy it? So -1 goes right up there in the table. F of -3 is -1. Okay, so it's going to take some time for us to fill in that table, and we will spend that time in just a moment. But in terms of thinking of the graph of f, like the two problems we just did, we have the graph of f prime, we want the graph of f. F of 0 was given as how much? Sorry, f of -4 was 0. Okay, so I'm going to draw here in red. F of -4 is 0, so the graph starts there. Remember how we had the freedom to start it wherever we wanted? We don't on this one. Starts there. And how much is f of -3 we just decided? Is -1. So the graph f prime has those 2 points on it. Let's see if at least the rough sketch we would have come up with would have done something like that. What's true about these? I'm sorry. This is f that we'd be graphing here in red. So what's true about all these green values? They're all negative. Remember, the first thing we're looking for is positives and negatives. It's a lot to keep straight, I know. So the first part is negative. If f prime, this picture, is negative, what is f doing? It is decreasing. So the 2 points that we've got here in red indicate that the function is decreasing. Yeah, but more than just saying, well, you know, it decreases to some place, we can say exactly where it decreases to. It decreases to that point right there. And so this, I think, is the little detail that Nikki had caught before. We can be precise if we can do areas. The areas tell you exactly how much the function changes by. So it starts at the first point, ends at the second point, and it was concave up in that stretch. Right? So we can be very accurate if we have areas. Okay, let's do one more of these. We'll get started together on the next one. Integral f prime of x dx equals, we're going to put two numbers on there. You guys know what two numbers we're going to pick? -3 to -2 is the easiest way to go. -3 to -2. That's just inching one step to the right. According to the theorem, this is really f of minus f of negative 3. The value of the integral is an area, which you can calculate. F of negative 2, you don't know, but you want to find it. F of negative 3, you just figured out. So with your neighbors, take your time as you find these areas, and take your time writing down lots of those kinds of equations. See if you can fill in the rest of that table. Okay, so we'll come back together. I've got my answers filled in red in the table. We ended up using the fact that the area of a circle is pi r squared, so the entire circle is 4 pi, but we had to cut it up into quarters, right? Going 0 to 2 and then 2 to 4. Okay, so this is the fundamental theorem, and you can see how the fundamental theorem can give you exact values of the function f. If you are looking at f prime and you can find areas, you can tell me everything there is to know about f with as much precision as is possible. All right, let's take a look on the next page, number 12, and I think we're up to Jeremy. Okay, so we're trying to get information about f, given that f prime of t is ln of t. Okay, we don't have a picture in this case, so we might just think, well, why don't we just try to go directly at it? Am I interested in doing a derivative of ln or an antiderivative of ln? Antiderivative, right? Given that f prime is ln of t. Okay, ln of t is a fairly simple, straightforward, familiar function. Can you name a function whose derivative is ln of t? Someone who's tried, that was quick. We have the, we have the reference sheet, right? The derivatives reference sheet. I think it's page 3 of the packet. So the derivative of ln of t is in the table. It's 1 over t. We got to vote for e. I heard a 1 over. Is there any function that we took a derivative of where we got as an answer ln of t? It does, but it's the ln of a number instead of ln of, yeah. No, that's good. Okay, so even though it feels pretty straightforward, oh yeah, we've seen ln so many times, we've never taken a derivative and had ln of t be the answer. So unfortunately, we don't have the ability at this point to figure out what f of t is. If we could just find f of t as a formula, as a rule, then this question would be easy. But we don't have a way to do that yet. It is coming. But for right now, we're going to use there is a function whose derivative is ln of t. We will see it soon enough. But for right now, we're going to do our fundamental theorem again. So let's start writing it down. Integral f prime of t dt. Okay, given the information in this problem that f of 1 is 4, and we'd like to find f of 2, what numbers should we put on our integral sign? 2 and 1. Okay, according to the fundamental theorem, this is really equal to f of what? 2 minus f of 1. Okay, which of these three things is what we're after? Is the f of 2. That's what I want, so we're just going to copy that. How much is f of 1? It's 4. It's given. How much is that integral? Calculator is going to tell us, right? That's just an area. So let's use the calculator to find that area. So I'm going to look at the picture. I like to see the picture. So I'm going to graph ln of x. And the standard window is okay, but the action, well, maybe it's fine. Seems like the action is going to be kind of happening in a small part of this big window. So how about we change our window? Let's see, x min, I guess we can start at 0. And what's the biggest x value we're interested in here in this problem? It's 3. Let's go out to 4. Okay, and then the y values, well, it seemed like everything was happening in a very compact space there. So I'll try -2 to 2. And if it's no good, we can change it. At least we should have a big, like the picture, the graph should take up more of our window than it did before. All right, that looks pretty good. Okay, how am I going to ask the calculator to find the area between 1 and 2? It's inside of calc, so we do second calc. Number 7. It's important to type the numbers in the same order that you wrote them on the integral sign here. Lower limit is 1. Upper limit is 2. And then we hit enter, and it will shade and tell us the area is about 0.386. Well, there you go. That's the value of this integral. Or at least it's a close enough estimate. So then how much is f of 2? 4.386. There we go. Any questions on that? So you can find out anything you want about the antiderivative of ln of t. I don't know what the formula is. I don't have a nice function that just says f of t equals blah. But you can find any value of the function that you wish by doing one of these calculations. It might feel a little bit cheating because the calculator is helping us with the areas, but if we believe the calculator is good at that, then we can find any point that we want to on the graph of this unknown function, this f of t function. Topher. Calculator to do what? To give us a derivative. The calculator can find, this calculator can find numerical derivatives, but it doesn't know that the derivative of x squared is 2x. Okay, if we followed the same thing that we did before to find like on the previous problem, to find f of 3, what would our two limits be? Like we'd go 2 and 3, right? That's what we did before, just inching to the right. You don't have to pick 2 and 3, you don't have to inch. In fact, I would encourage you to pick the number 1 every time in this problem because it's a nice number, right? Any other number that we get is going to be an estimate. So no need to kind of compound the estimation error. So see if you can find f of 3 and f of 0.5. If you finish, there's a challenge problem down below. And for the 0.5, in what order should we put the numbers on the integral sign? So like 0.5 to 1, right? Because we always put the smaller one at the bottom. You know what? I'm feeling kind of bold. Yeah, let's try the other way. Yeah, Chris. It will be. So let's see if this works. So according to the theorem, this is really f of which one goes first the way I've written it, which is like the wrong way. 0.5 minus f of 1. Okay, fair enough. This integral we're going to do on the calculator. Let's see what happens. So Josh had just asked, is there a way to get it to redraw the thing because I want to really see the new shading? Yeah, just add anything into your original equation and it'll think it's different. So if you need to put a +0, that's enough to convince it it's something new. And now I'm looking for the integral from 1 to 0.5. Okay, right here is the number 1. 0.5 is to the left of it. Is that area going to be a positive or a negative? It's going to be negative because it's below the axis. However, we put the numbers in the wrong order. So how do you flip them and put it in the right order? You negate again. So the value of this integral is going to be what kind of a number? It's going to be positive when all is said and done. It's two negatives. The area down here should be negative because it's below, but because I put the numbers in the wrong order, everything is opposite what you'd expect. So it's actually going to become positive. So if we do second calc and then 7, and I'll do 1 up to 0.5. I actually think it shades. Does it shade it left? Yeah, I think it still shades left to right. I think. Yeah, so positive 0.153. So this integral is 0.153. F of 0.5 I don't know, minus 4 every time, so just stick the 4 on the other side. Any questions on this? So this is kind of interesting to me. I feel like there's something powerful happening here. Somebody took a derivative of some function and they got ln of t. We have no earthly idea what that function was, right? And we don't have any way to find it at this moment. But what does it mean to really know a function? Well, it feels like if you can find f of 2 and you can find f of 3 and you can find f of 0.5, you could plot all of these points and 100 other ones and look at a pretty darn good graph of the function that you really don't know what it is, right? You could find as many points as you want. What does it mean to know a function? Feels to me like it means you can evaluate that function anywhere you want, and we can. Right? As much patience as you have to just do these calculations over and over again, you can plot as many points as you want on the unknown function f, you draw a picture, and get a real good looking graph. So I think it's kind of a nice idea, this fundamental theorem, and then use it in conjunction with the graphing calculator area thing. Okay, so with the 15 minutes remaining, Nikki, was there a question? Let us know. All right, so there are 6 problems right here. And what you're going to do is sketch an antiderivative on the same axes. So what we're saying is that for each of these, you are looking at f prime, and we want to see the graph of f, just like the 2 things that we started with today, okay? There is an answer key at the back. However, all 6 answers, you'll see them as soon as you flip over to the next page. So as you do one, I'd encourage you to very carefully flip to the next page. Try to block everything except the thing you want to see. Does that make sense? And I'll walk around and help each other out. Yes?
No, still not.
Okay, you'll let us know. All right, see how far you can get on the 6 graphs there.